the sum to infinity is an inherently peculiar idea. The fact that we're adding some number or some sequence of numbers together infinitely, such that there are infinite terms, raises quite a few questions. Well, I'm Daniel from CMC Learning. Today we're going to have a look at some of the applications of summing to infinity, but also how we can even do it in the first place. So let's get started. Let's first consider when we should be doing, or when we can be doing the sum to infinity. Let's first start with the most simple of series. So a series being the sum of terms in a sequence. Let's start with an arithmetic series. So one such that the first term is a, and the second term is a plus some difference. And as we continue with more and more terms, we're going to be adding, essentially, more copies of this d, which is a difference. Of course, remembering that we define the nth term of this series or sequence as follows. So a plus n minus 1 multiplied by d. In a previous video, we did describe how we can write this series, this arithmetic series, for any n terms. So we managed to derive that the sum to n terms is equal to 2a plus n minus 1 multiplied by d. And this equation actually does simplify quite a bit. It also demystifies a little bit. Essentially what this entire topic is concerning is if I add these terms an infinite number of times, what am I going to end up getting? Well, it's something we can check just by sort of multiplying these terms out. Let's just have a look. Get as our first term, if I multiply this n divided by 2 into my bracket, I get n multiplied by a plus n multiplied by n minus 1 multiplied by d. So let's have a look at what exactly happens when we set n to infinity. As far as many students, at GCSE know, saying n to infinity is just saying n to some really, really large number. That's definitely a good way to sort of process what is happening. If we have a look, if n is tending to infinity, then this first term is also going to tend to infinity, depending on the sign of this value a. For example, if a is negative, this will tend to infinity in the negative direction. The same thing can also be said for this value of d. So depending on whether or not d is positive or negative, we can see that we're multiplying n. We're going to get an n squared term minus n multiplied by d. Essentially, as n tends to infinity, we're going to find a lot of infinities in this case, and if anything, it's not really resolved. And there's a good sort of lesson in here, if you will. Essentially, with arithmetic series, sum to infinity isn't all that special. If we just end up adding or taking away these terms constantly over an infinite number of times, we're just going to get plus or minus infinity. Essentially, what we have here is a diverging series. So it's diverging from any given value. The series, however, or the sum to infinity, does get a little bit more interesting when we consider geometric series and geometric sequences. So let's have a quick recap with the geometric sequence. We define the nth term as a, which is our initial term, multiplied by r, which is this multiplicative difference, to the power of n minus 1. If anything, r can be 2. If my first term is 1, the sequence will look something like this. So 1, 2, 4, 8, and so on and so forth. So that's all and well, and the question definitely stands. What happens if I add these terms infinitely? Well, we can even have a look at that example I just posed. 8, so on and so forth. Well, here, given what we've looked at above, if I just add an infinite number of these terms, they're always going to get bigger. They're always going to be multiplied by 2. Well, in that case, I'm just going to end up at positive infinity. If I'm adding an infinite number of these terms, it's going to tend to infinity. We can also ask the question of having a negative value of r. So say I do start with 1, and my next term is minus 2, then 4, then minus 8, and so on and so forth. Well, in this case, the argument can be made, well, if I add these first two terms, I get for example, get minus 1. If I add these two, I get a minus 4. If I keep adding them on and on and on, it's actually quite a good way to see it. We're going to get some value that also tends to infinity. So this also diverges. And the reason why it diverges, the secret lies in this value of r. Let's have a look. These numbers are just going to get bigger and bigger and bigger. But we need to ask ourselves, do there exist a subset of values of r such that the following term is not greater, but instead smaller? Well, let's see. If I start with some term 5 as my first term, the only way I can get a value smaller than 5 is by multiplying by some number less than 1. Say r was 0.5, my next term would be 2.5, 1.25, and so on and so forth. This also, however, doesn't rule out negative values of r. So say I do start with 5 again. My value of r was minus 0.5. Or I end up with something like this, so on and so forth. Minus terms for every, if you will, even value of n in this case, of our sequence. So, we have a look at these terms. We can sort of restrict values of r such that our series is not diverging, but instead converging. We can write that quite nicely with this modulus, which we also have made a previous video on. Essentially, this modulus takes the positive value of any number you give it. If r, for example, was equal to minus 0.5, then mod of r, that's how we say it, mod of r would be 0.5. And if we really wanted to, we could write out this inequality in a somewhat more explicit way. We can say that r goes between minus 1 and 1. These two inequalities represent the same thing. Also, be sure to note that this is not an equals to. This is sort of just a less than or greater than. Okay, so we have some condition where our sum is essentially converging. It's converging to this one value. You could even plot this on a set of axes, which is quite a nice exercise. Say each of these little squares is a value of n, for example. Let's say I start with some value up here for a, or we can actually put it up here. Well, when n is equal to 1, my next term is going to be half, for example, if r was 0.5. After that, my next term will be half of that, then half of that, and then half of that, and so on and so forth. We can already see after a few values of n, we've converged very closely to this x value, or this y is equal to 0 line. The important thing is, though, if I'm dividing some number by 2 an infinite amount of times, will that number ever reach 0? Well, the answer is no, because we cannot just divide something and get 0. It needs to sort of have the opposite action as well, but it can get really, really close to 0. And that's the idea of convergence. We're essentially 0, but we're not exactly 0. And this is why it's interesting. So say I wanted to do the sum of these terms. I'd be adding this term to this term to this term. After a certain number of terms, I'm just adding essentially 0 to my number. So you could even think about it to some sort of decimal point of accuracy. We're just adding really, really minute amounts of, to this number. So in a way, after a certain value of n, this essentially becomes one number. It converges to one number. So let's have a look. If we write out the sum to n terms for an arithmetic series, we can write it out as such. In fact, there are two equations that we can write, as shown in one of our previous videos. We have a look at each of these. One of these is technically preferred over the other when doing such sums to infinity. However, they both should yield the correct answer. These are both essentially identical. Let's work with this second one. In this case, it tends to give nicer results. We want to consider, a formal way to write this, we want to consider the sum to infinity of this term over here. And we can see that that replaces the index of n, so we want to see what happens when n tends to infinity. Well, again, we can stick with some nice notation and introduce the idea of limits, which perhaps some of you may not have covered yet, but will come up in the, actually it is sort of year 12 differentiation content. It does come up. It's good to get comfortable with what the limit actually means. So let's write something. Let's write the limit of, the limit as n tends to infinity of, for example, let's maybe just have a look at this r to the power of n term. If we look at every other term in this sum to infinity, it's all independent of n, so we don't necessarily need to consider it. It could be helpful to just consider what happens to this term and then see how it changes the rest. So formally, we can say something like this. In reality, we can really only look at this term here. And remember that all of these limits, both of these limits, they're coming with the condition that r, or mod of r, is less than 1. So a number between -1 and 1. Now if I'm doing that, if I'm doing this sort of sum of terms that are just going to get smaller and smaller and smaller, well, eventually I'm going to converge to something. And you can sort of look at that as sort of thinking, what does this term look like? So if r, for example, is 0.5, even if I do on my calculator 0.5 to the power of, let's say, something like 75 or even 100, we can see that we're going to get a very very small number. A number so small such that it is almost negligible. So we can say that in the limit, as n tends to infinity, r to the power of n is just equal to, let's write it out, r to the power of n, we can say that this is just equal to 0. Essentially, we've added these terms so many times that it becomes 0, or essentially the nth value is 0. And we can have a look at that in the sum, that that term sort of persists. So in this limit, we can just rewrite the sum to infinity as a multiplied by 1, and then minus 0, well, we can just leave that as 1 minus 0, which just gives us 1. And we notice that this r term is unchanged. Well, this r term was independent of n, so it's not affected. And this gives us the sort of much loved equation for the sum to infinity of a converging series. And it's very important to note, as always, that the mod of r is less than 1. This is the only way this is possible. Let's say, for example, I had a geometric sequence such that my terms were 3, 6. Or actually, no, we need to do a converging. So let's do 10, 5, 2.5, 1.25. on and on. Say I wanted to know the sum of all of these terms as they're getting smaller and smaller and smaller. Well, I can employ my new equation. Here I see that a is equal to 10. My value of r is equal to 0.5. If we plug this into the equation, let's have a look at what we get. We get the sum to infinity being equal to a, which is 10, divided by 1 minus 0.5. In this case, this is 10 divided by 0.5. That's the same as multiplying 10 by 2. So left with 20. And of course, I wouldn't encourage anyone to try this on their calculator. If you were to add maybe just these terms here, we can see we're getting about, so 10 plus 5, 15, plus 2.5, 17.5, plus this term here, 18.75. We're getting really, really close to this value of 20. Even as we add more and more terms, the following terms from here, we're getting really, really close to 20. And after adding an infinite number of terms in this series, we will end up getting to 20. So yeah, I hope that is a somewhat interesting look as to why, or how, or where this equation comes from. I think is better. It's also a good sort of place to employ these limits. It's definitely good to get comfortable with these by the time sort of A levels come. If you do have any questions about any of the content covered today, then do let us know in the comments below, and I'll see you guys in the next video.